Okay, so we're looking at, starting off from where we left, which was with polysaccharides. They're the really, really long ones that are insoluble. You ever wonder why paper is so good at absorbing water? Well, it's because it's cellulose. And cellulose is covered in hydroxyl groups that have absolutely no problem with water hanging around. So if you stick paper in water, the paper absorbs the water, but the paper does not dissolve itself, because the paper consists of cellulose polysaccharides, which are far too large to dissolve. So, they've got no issue getting soggy because they're capable of hydrogen bonding and dipole-dipole, but they're not the biggest fans of dissolving because they're far too large. Okay, ring chains. What you're looking at here is glucose. Glucose is a polyhydroxyl aldehyde. So if you note here on the end, you've got carbon number 1 has a double bonded O on it. So that's a terminal aldehyde group. The carbons in the ring chain form are listed. That's carbon number 1 here. The C is covering up the 1. Not my fault. I just rated this from Google image search. 2 through to 6 hanging off the side here. And there's 1 through to 6. When it joins in its ring chain form, carbon number 1 is joining through to carbon number 5. So here's carbon number 1, and we're going through the double bonded O through to carbon number 5. This clearly shows you that a saccharide chain is, in all honesty, quite flexible if it's able to join together to make a 5-membered ring. And in solution, so in water, this glucose will swap between both the straight chain and the ring chain form. Now, if you take a look here, again, we've got glucose on the left in the straight chain form. Note the pink aldehyde group at the top on carbon number 1 and the blue aldehyde hydroxyl group on carbon number 5. Now you can see here carbons 2 and 3 in brown. They're the site of where it's going to bend around from, so they're going to stay straight. And then the ring will bend around, and we're looking at the one in the middle here, and we start bringing the aldehyde group close to that hydroxyl, which is with carbon number 5. And then there's an exchange. So the hydroxyl with the blue hydrogen, it loses that hydrogen. The hydrogen will go onto the double bonded O with the aldehyde group and become a hydroxyl group, and the double bond, which was originally attached to the oxygen in the pink, goes to the oxygen in the blue, and then you get your chain, your ring form, not your straight chain form. And it's going to go between these two products via that intermediate, constantly backwards and forwards. Now here's the thing. If you want to tell the difference between an aldehyde and a ketone, even a polyhydroxyl aldehyde or ketone, they're still an aldehyde or ketone, your standard silver mirror test applies. So you use Tollens reagent, and in the presence of an aldehyde, it will react to form a carboxylic acid in a silver mirrorable form. So if you use glucose, for example, with Tollens reagent, you're going to get yourself a silver mirror. And it'll confirm the fact that it's a polyhydroxyl aldehyde.